Hello, welcome to the core of our MCMC lecture, the Metropolis algorithm. In this video, you will learn the procedure of this particular algorithm and understand the way it generates samples. Metropolis algorithm samples from a target distribution P of set by constructing a homogeneous, reversible, and ergodic Markov chain. And we will talk about why is this the case later. To achieve this, we first define a proposal in the form of a transition probability Q of set given set of tau, by, for example, the probability distribution for the next step conditional on the current step. Further, we combine this proposal with a certain accepting or rejection criterion. Here are the procedures of Metropolis algorithm. First, we need the proposal to be symmetric, which has an equal transition probability between any two states. Then, we need an initial point to start the chain. At each step, denoted as set of tau, we generate a candidate point set star, conditional on the current step following the proposal. Then we calculate the so-called acceptance ratio, A of set star to set of tau, by taking the minimum of 1 and P of set of star divided by P of set of tau. Apparently, A is a scalar between 0 and 1. To decide whether to accept or reject the candidate point set star, we generate another random number u from the uniform distribution over the interval 0 to 1. If u is smaller than the acceptance ratio A, then we accept set star. That is, set at tau plus 1 equals to set star. Otherwise, we reject set star. That is, set at tau plus 1 remains the same as the previous step. After the decision of acceptance or rejection, we move to the next step and generate a new candidate. We calculate the acceptance ratio and we make the decision of acceptance or rejections, and so on and so on. From the procedures, we can see that the Metropolis algorithm works through random attempts of moving in the state space. The acceptance ratio indicates how probably the candidate sample is with respect to the current sample. If P of set star is higher than P of set at tau, that is, the candidate sample is more probable than the current point, the acceptance ratio is 1. And we will always accept this movement. If P of set star is lower than P of set tau, then the candidate sample is less probable than the current point, and we will sometimes reject the movement, and the smaller the P of set star is, the more likely we are to reject the candidate point. Over here you will see an animation where we show a univariate target distribution as an example, and each attempt of a movement is indicated by an arrow, where a green arrow represents acceptance and a red arrow represents rejection. As we can see, when the arrow points upwards, that is, the candidate point has a higher probability than the current one, we will always accept such movement. However, when the arrow points downwards, that is, the candidate point has a lower probability, we decide whether to accept or reject the candidate based on the acceptance ratio. The larger the drop, the more likely we reject it. By doing this in an iterative way, we can get large number of samples from high density regions, while occasionally visiting low density regions. We claimed in the beginning that Metropolis algorithm samples from P of set by constructing an homogeneous, reversible, ergodic Markov chain. Here let's see why it is this the case. First, it should be noted that Markov chain we are talking about here is not the proposal solely, but the combination of the proposal with the acceptance or rejection criterion. They work as a whole, and the transition probability from set to set prima is calculated by the product of the proposal and the acceptance ratio, which means that the transition is only possible when the new point is proposed as well as accepted. Then obviously this Markov chain is homogeneous, since the transition probability is independent of the step tau. Then it is also not hard to prove that it's reversible, or we can also say that satisfies the detailed balance property. So please feel free to pause the video now to have a look at the procedure. So the detailed balance property guarantees that when we start from the target distribution and write the Markov chain, we can stay on the target distribution. Finally, following the sufficient condition of ergodicity, it is easy to find that when this condition is satisfied, that is, that the target distribution has non-zero probability over the whole state space, and the proposal has non-zero probability of moving from any state to any other state, the established Markov chain is ergodic. This enables the established Markov chain to reach the whole state space. Furthermore, we can compare Metropolis algorithm with the rejection sampling method. If you haven't well understood the Metropolis algorithm, you might skip this slide and watch it later. We can see both methods make use of a proposal to generate candidate samples, and the rejection samples uses an envelope distribution to generate a sample independent of previous ones, whereas Metropolis uses a transition probability to generate a sample dependent on the current state. Besides, both methods use a uniform distribution to generate a random number. The one in rejection sampling depends on the probability of the candidate point, whereas the one in Metropolis is distributed over 0 and 1. Finally, both methods rely on a certain criterion to decide whether to accept or reject the candidate point. Rejection sampling compares U with the probability of the candidate in the target distribution, whereas Metropolis compares U with the acceptance ratio, which highly depends on the change in probability from the current sample to the candidate sample. So, all right, we have talked a lot about the theory of Metropolis algorithm, and our next step is to implement it and play with it with the codes. Here we show the example of the Python codes corresponding to the procedures, and you can find more details in the notebook and learn to apply this method to general samples.